In this tutorial, I will explain how to read TensorGraph, taking you from the basic idea to complicated model. At the end of this section, you will know how to interpret TensorGraph, just like this one, which is shown on the screen. Before going to the final stage, I find it useful to talk about the basic idea of machine learning first. Prediction is simple with one variable and one target value. When you want to predict the second target value, we find the weight in the first observation and then plug this weight into the second one. And what happened when we have more data? Our approach did not work as the first weight did not fit to the second observation. So we need a bias. We can solve the problem manually with few features or variables and few observations or rows. Things will quickly get complicated when we have a lot of data that we need computer to speed up computation and accuracy. That's why machine learning taking into account. To begin, we start with a very simple hidden network, one hidden node or neuron. This neuron takes three inputs: data, weights, and bias. It sums up weighted inputs, add bias, and use activation function to compute the result. Depending on the type of problem, you may have different activation functions. To simplify the calculation, often bias term is represented as a weight with unit input. To illustrate this simple perception, let's get started with an example. So in this example, we need to find weights such as with a given input, it will give the results as close to the real values as possible. So we use step function as an activation function. The learning rate is set to 0.4. You can modify this learning rate to any number you want. And the initial weight vector is -2, 3, and 1. And here is algorithm to show our problem. And let's see how this neural helps us find weights. So the input value will be multiplied with the weight vectors, and then this value will be summed up to produce a scalar value. And this scalar value here, as you can see, is -2, could be passed through an activation function, the step function. And the step function will give the result of either 0 or 1, depending on the input. If the input is less than 0, it will give you 0. And if the input is greater than 0, it will give you 1. So in our case, input is -3, so it will give you it will give us the predicted value is 0. And then we compare the predicted value with the true value, which is the output here, number value here, because the predicted value and the true value is no different, so it means it's equal to 0. And then we do nothing and move to the next step with the second data. So the second data, we're fetching the second data to the neural, and we perform the same calculation, and at this time the scalar value is 1, and then the predicted value the scalar value is -1, so it will give us the 0 as well. So we do nothing in this step. So fetching the third row data and perform the same calculation. This time a difference is here, so the scalar value is 1, so the predicted value is then 1. So at this step the the predicted value is different from the true value, so that means an error occur. So we need to, at this time, we need to update the weight vector so that with the same input it will give us the correct result. So with the expected result which is 0, not 1. So we need to update the weight vectors here. So how to update the weight vectors? So we need to calculate the change in weights by taking the input vector. We multiply the input vector with the learning rate, which is 0.4, and the error, which is -1. Once we have the change in weight vectors, so the new weight vectors will be calculated by adding the change in weight vector with the existing weight vectors. So we have new weight vectors, which is -2.4, 2.6, and 1. So we continue our operation by fetching the last data, the last observation into the neuron with a new update weight vector. So at this step, perform some calculation, we have the correct result. So after the first, we can see that after the first epoch or first iteration, when we go through all the row in our data or all the observation in our data, we have our final weight vectors, which is -2.4, 2.6, and 1, but we don't know if this vector correctly classify our target values with all given variable because we haven't tested it yet with the previous data. So we need to run it again. So run it again, putting the first data into with the weight vectors. So we have 0 as the predicted value, which is correct, nothing changed. We go to the second row and give us this predicted value 0, again this correct, nothing changed. Go to the third row. At this step we can see, so the predicted value is 1, which is different from the true the value, which is 0. Cool. So we need to update the weight vector again with the same calculation or the same formula. We have our new weight vector is -2.8, 2.2, and 1. So apply this weight vector and then move to the next data, and then at this time the final output is 1, which is correctly classified. We do nothing, and then we after the second iteration we can see that we have new weight vector, and we have the same question again. We don't know if this weight vector is good one, so we run it again with the data set. First data 0, predicted value 0, and true value 0, good. Second one 0, 0, good. Third one 0, 0, good. And the final one 1 predicted value and 1 with a true value. Okay, everything is good. So as we can see, after training up 2 epoch, our weight vector is -2.8, 2.2, and 1 gives the desired result, which correctly classify our target value. And the question is, how can we visualize our algorithm so that we can check if any part of the programming is correct? For example, when calculating the changes in weights, we have to multiply with input data, not the weight vector. So we answer this question by using TensorFlow to programming and TensorGraph for visualization. So in TensorGraph, each node is represented as an operation, and data flow between nodes is called tensor. So this tensor graph demonstrates exactly how the perceptual learning algorithm works. First, a weight vector is initialized. The second, the data is read from the input, and the weight vector and the input data will be multiplied and summed up to give a scalar value. Then the scalar value will be passed through an activation function. So this activation can compare the data with a constant, which is 0. And depending on the value of scalar value here, it will provide the predicted value here. And then the predicted value will be compared again with the true value and give us the error. And then at this step, if error occurs or different from 0, we compare the changes in the weight with the input of 0. Remember that the change in weight takes 3 inputs: error, the learning rate, and the input data. So in some way, if this input data did not dry up correctly with to further multiplication, instead of input data, it get the tensor board or it get from the weight vector. We know that from the tensor graph here. So come back to the changes in weight vector. It takes the errors at input, multiply with the learning rate, and then the input data. When we have the changes in vectors, and the new weight vector will be calculated by adding the changes vector with the existing weight. So this operation, we can see the add operation is here. So at the final step, we updated the weight vectors, and then the weight vectors will be updated to the initial weight vector here, as see on the orange line. One good thing about the tensor graph is that we can see in detail how operations work on this model by double clicking on the, for example, on the predicted value. You double click on it, or you click on the plus sign here to see the detail. So if this one, we can see the activation, how the activation works. We switch if the switch is full, true, merge, compare with a constant of 0 or 1, and give a scalar value. A final scalar value is here. And you double click again to zoom out. So with similar approach or similar interpretation of the previous algorithm, I think you can start diving to the more complex model. It's very similar to what we have learned, but basically we can simply interpret this tensor graph as follows. So taking from the input data will be passing to the LSTM layer. This LSTM layer will initialize a weight function, and the weight function will combine with input data and provide uh, the data for the dense layer, which is the another hidden neural network. And this dense layer will perform another function as well, and then it provide the predicted value. As you can see, the loss function here, the predicted value, and the loss function can get the predicted value combined with the existing the true value and some initialized sample weight, and then it calculates the error. And because in our previous example we calculate the error and update the change by a simple function, but in this complex model they have an optimizer function to calculate the error and the changes in the weight. But finally what we expect is the weight vector, so that when we input our data into weight vectors, it will give us the results as close to the truth value as possible. So as you can see, the output of the training here, it gives us the weight vector, which will be reused in another hidden network layer. And then as you can see, the orange line here, that means training will keep updating the weight vectors in this layer multiple times or multiple epochs.